So my name is Mandar. I work on Istio at Google. And if you're here for fine-grained mesh telemetry, then you're in the right place. Otherwise, that is still what you're going to hear.
Hi, my name is Kuat. I also work at Google on Istio.
And the third one who worked on this, she couldn't come. So before we start, since this is about service mesh, we're just going to take care of some preliminaries. Why service mesh? I think that is probably covered a bit by now, but I will still cover it a little bit. Why do we need granular telemetry? That's another thing we have to cover. What is available without the work that we did, and then what we have added. So we'll kind of go through that. So now consider the graph on the right. And consider that it represents just a monolith. Every node in the monolith is a module, and every edge in the graph is a function call. Now, when we decompose the monolith and we go to microservices, the easiest way to just draw a border around a module and say, OK, that's my service. And now the picture still looks the same, except all those edges now are going to be RPCs. They're going to go over the network. And then that's when we move to Kubernetes, for example. So essentially what we have done is we have moved from something that was very fast, very reliable, and very secure to something that's not as fast, not as reliable, and not as secure. An in-memory function call simply does not have that many modes of failure, right? You make the call, and the call goes through. Not the same with an RPC. So we introduced a whole class of problems that did not exist before. And of course, we know why microservices are good. I'm excluding that part from here. But as far as the call is concerned, we actually did take a few steps back. So what service mesh tries to do is it tries to restore some of those qualities that we lost when we moved away, when we moved towards microservices. There are many service meshes, but my favorite is Istio. And of course, Istio is based on Envoy. And we inject a sidecar, and Pilot, which is the control plane, configures Istio. So now we'll just see how service mesh is realized. So first of all, we start with this simple picture. Just 3 services. There is product service in the middle, shopping service, and a shipping service. The direction of the arrows indicate the calls. And these boxes could be pods or workloads, but for this discussion, consider that these are pods. And now they're just calling just normal, nothing special here. Now magic, and we inject Envoy sidecar proxies in each and every pod. We have to make sure that any traffic that previously flowed directly between the applications is now mediated through the proxy. And there are many ways to inject this proxy. There is IP tables magic. You can use HTTP proxy variable, and there are other ways too. As long as you use one of those ways and get the proxy in the middle, we have a place where we can implement functions of a service mesh. So the 3 pillars are routing, security, and observability. We're going to talk about observability for the rest of the talk. A note about upstream, downstream nomenclature, that is consistent with Envoy because that's what we use. The arrows are pointing upstream. So product service is upstream of the shopping service, and conversely, shopping service is downstream from the product service. This does not, so now we need to continuously and dynamically configure the data plane. the proxy is the data plane. And then we add the actual control plane on top, which is going to dynamically configure it. It uses the XDS protocol to configure Envoy. That protocol is defined by Envoy. There are many control planes that are available. Istio Pilot is, of course, the OSS Istio control plane. Cloud vendors have their own. So, for example, Google has Traffic Director as our control plane. We are going to talk about Istio, though, for the rest of the talk. So, kind of the purpose of this talk, right? What questions are we trying to answer when we look at a service mesh? So there are certain questions that are at kind of a whole mesh level that SRE monitoring the entire mesh may ask. And these questions are of the form, who's talking to whom? Are there any links, or are there any services that are more loaded than others? Do I see like many errors somewhere? And it really looks like the service graph that is actually in the picture. So that's the view that you're interested in. When you go down to a service owner's perspective, now you're interested in specific activity that happens around your own service. In that case, you do on that cluster. So all those would be client-side cluster stats. On the other side, the server-side stats are captured by listener stats, and these are called downstream stats. In both these cases, we have used the Prometheus format to express the statistics with its dimensions. So let's first consider client-side stats. So upstream request total is like one of the standard stats that you can get. It is dimensioned by two quite useful dimensions already. One of them is cluster name, and the other one is response code, or in this case, it's a response code class. If you apply a rate function on it and track it over time, you can get rates, and then you can know what to expect, but what is the norm. And because there is the response code class dimension, you also know the error rates and success rates and like 4xx. So if the client is doing something wrong versus server is doing something wrong. The other part is quite interesting because that dimension is the cluster name. If the control plane has used a reasonable name for the cluster, then you will actually get very useful stat here, right? The cluster name is actually pointing to the destination of this traffic. In this case, in this example, it's going to product SVC. Though, okay, well, it should have said, no, that's right. It is going to product SVC. Now, if, is there, like, still what is missing? Maybe you want to know if a request ended up in a different availability zone, right? How would we add that dimension to the client-side stat? And it is not a very uncommon situation, right? In one cluster, you can have some endpoints from one availability zone, some endpoints from another availability zone, and you would still want to know where the traffic ended up. So how would you put that information there? So in this example, we want to have zone equals US West 1A, like that sort of information. If a dimension is a property of the cluster, then it is possible to add it in the stats. You can either supply this alternate stat name, and you can encode whatever you want in that, or you can just use the cluster name itself to encode whatever else you want. In order to do that, though, since it is done by the control plane, it has to be a property of the cluster so that the control plane knows what to put there. And since zone, in our example, is not a property of the cluster, because one cluster includes endpoints from multiple zones, that this dimension cannot be added by what is available here. So you really need some support from the data plane in order to do this. Now consider the other question from the server side. Who is calling me? So there is an analogous stat on the listener side called downstream request total. And it is also dimensioned by response code, so that's just like before. And the other dimension is listener. Now, listener dimension can be useful sometimes, but in this case, it's not really adding much value. It uses an IP address. Most services will just have one listener, and it is what it is, so it's not really adding a whole lot of information. And then the crucial point, the question that we asked earlier, who's calling me? That information is completely missing. So as you can see, the downstream stats are a bit sparse here. So Envoy native stats are, they have some coverage, good coverage on the client side, with still some missing parts as we saw, and less coverage on the server side. So it's very fast. It's purpose-built, but only turns left. So if there are any NASCAR fans here, they would probably get the joke, but that's fine. So we want something that can turn left, right, and still move fast. So just a unrelated to technology question, what can top a NASCAR, right? All right, yes, Formula One, okay. So the wish list that we want is we want to have peer-aware metrics, so we can dimension our metrics by peer properties. Like we said, like we saw before, the availability zone would be a property of the peer, so we do want to be able to dimension our metrics that way. In this case, we have dimensioned it with caller equals product. And then we also want to be able to dimension metrics by traffic properties, so headers or like anything else like that. Maybe use OpenAPI to classify something, put the request here. Now, some of these things are actually possible, so you can have like virtual cluster, and then, but it is quite tedious. It results in very large configurations. So we need something more. So how do we impart peer awareness to this flow, right? What are our options? There is actually a very simple kind of obvious option. Just send it in a header, right? So the simplest option is when the client makes a call to the server, it puts its own metadata in a header. It also puts an ID of itself in the header. So now when the call goes to the other side, server will know who called it and whatever metadata you packed. And then the server responds with its own information. So at the end of the call, both parties know who each other is. And now you can use this information to dimension metrics whichever way you like. This is a very, very simple protocol to implement, like few lines of code in most cases. It is fully stateless, but as with many stateless things, it is not really efficient. One of the things that you'll see in this protocol, the reason why it's not efficient, is because you'll end up exchanging the same information over and over. Right? Two pods are communicating. They're going to tell each other the same thing over and over, like thousands of times. That's going to add to CPU and latency.
So what Mandar described is an instance of a basic protocol, how to exchange metadata between peers, proxies. General scheme is that we start every proxy with a small metadata manifest that says which pod it belongs to, which namespace, what labels on the pod, maybe availability zone. Whenever two proxies communicate, they send this metadata in addition to the normal traffic. And that way, each proxy knows what the other peer is. So this protocol works for HTTP headers, but it has performance issues. But we have some ideas how to improve upon that. First of all, we split the metadata into key and the payload so that any computation that depends on the payload can be cached using the key, including the wire transfer. And second idea is that because we control both sides of the communication, we can upgrade the protocol to HTTP2. And HTTP2 has these nifty features like metadata frames. These are sent in addition to normal traffic, but they don't count. So that way you can associate metadata frames with either individual request streams or you can put it into connections. Unfortunately, not every proxy implements this. It's a very recent feature, so it has some downsides. So what about other protocols, right? So if you don't just use HTTP, what about TCP? So if you're willing to tunnel everything for HTTP using things like HTTP connect method or gRPC bidirectional streaming, then the technique we just described applies. But what about just raw TCP, right? Maybe you don't want to send everything for HTTP. So in this case, we resort to sending just raw bytes. And the way that this would work is that we put an extension into every proxy that with every connection over TCP, before we send all the standard payload, we just prefix the metadata as the first bytes on the stream. The prefix is length prefix, so the first thing is a header. And that way works for both sides. Unfortunately, has an issue, of course, because both proxies have to be expecting this thing coming so that they can disambiguate. So that has how do we make sure that proxies agree on this? So one idea is that we can make the control plane just tell the proxies that the other side is an Envoy sidecar. So that way, each proxy would know which connections are to Envoys, which ones are not. Unfortunately, that is it's complicated because you need to coordinate now between the magic injection and the control plane. And also, you have to implement this for every single control plane out there. And we also would like to keep all the choices of control planes here. And the second idea is that in a service mesh like Istio, all the connections are already wrapped into TLS because we have MTLS automatically enabled. So we can piggyback on that. And the way it would work is that as part of TLS, the first message you see on TLS is called client hello. It has a field called ELPN, which is an extension to TLS, and it's basically application layer protocol negotiation field. It's a list of strings, and we can insert a special string there called Istio2, which is designated for a protocol. Then the server replies with its own hello. It also has a list of protocols. The two proxies must agree on one of them, and that has to be the first one. So if both proxies see that they support this protocol, they will choose it, and the handshake succeeds. So in this case, we can rely on the successful TLS handshake to basically establish this common truth between them. So we just proceed the normal TCP prefix. So let me just step back a little and remind you why we're doing all this. So we're doing this work in the context of evolving Istio telemetry from an architecture where we had a central service called Istio Mixer that be a telemetry collector and processor. Every proxy would send to this service, and then we run extensions inside Mixer. So there is a stats extension from which Prometheus scrapes all the telemetry in the cluster. Istio mixer also runs a cache where it pulls metadata from Kubernetes and it joins this metadata with all the data coming from the proxies so that we can attach all these fine-grained metrics. And the new architecture that we're trying to evolve is where we don't have any more Istio mixer. So every extension runs directly in the proxy. So that means we have no longer cache. And the way we rely on the metadata exchange is that we can spread this metadata around the cluster without maintaining a central cache in each proxy. We also would like to leverage WebAssembly. So as part of ongoing work is to develop WASM support in Envoy. So if you don't know what WASM is, it's an open standard that allows you to run spread in portable binary format for running extensions in a safe, isolated environment in a sandbox. You can compile to WASM from many languages, including C++, TinyGo, Rust, whatnot, JavaScript, of course. So our team has been investing a lot of work in building this support in WASM. So we are working in a repo under Envoy work called Envoy WASM. That's where we're building our sandbox extensions. As part of this work, we're also defining a new filter sandbox API. So what that means is that we would like extensions to be written against this API so that you can run them inside Envoy. So the basic architecture now looks like this. You have Envoy. We run extensions inside Envoy in process. Envoy still does all the proxy-related work, like protocol parsing and all the networking features. But it also calls back to the extensions that are loaded into Envoy. The extensions must be written against the C bindings that we supply. It's basically the sandbox API. What that allows us is that we can either compile them directly into Envoy, it's a method which we call non-VM. So these are just statically linked libraries in Envoy. Or you can compile it to WASM and then load them dynamically using any of the WASM engines, for example, V8. So that allows us to make a choice between whether to compile them in or to run them dynamically. The API is very basic, so what it gives you ability is to subscribe to the normal filter-like events. Whenever a request is processed, you can listen on headers, you can listen on data, you can listen on TCP connections. We also provide a shared attribute context, so it's a context for anything request-related. That way extensions can exchange data between each other. We also allow you to make side calls, so you can call out using gRPC or HTTP if you want to. And finally, we expose the native stats and login subsystem from Envoy so that will give you the raw native performance power. So the way it would work in this model is that we have this Metadata Exchange extension that implements the protocol. It reads some stuff from the node metadata in Envoy that includes the peer metadata. It also writes stuff to the context using the data that it sees on the wire. Then the next extension kicks in, and it's a stats extension. It reads the data that was written before, and it also reads all the other request data, and it emits statistics. So the way it would, so it's a bit of pseudocode, but you get the idea here. It's standard things you would normally do in metrics-related code. You have to create a metric. You have to compute labels for dimensions. You can pull data from the peer. You can find what the pod name is for the peer. You can also pull data about the request. And finally, you call out to the stats subsystem to emit the metric. There are a few gotchas you have to be aware of because this is still work in progress. Because we inherit the stats subsystem from Envoy, we get some of the performance problems that comes with it. For example, it was built from StatsD, so it means all the labels are linearized to a single long string. So whenever you have to scrape it with Prometheus, it has to be regex parsed. And the second thing is stats subsystem has this assumption that all the stats are associated with XDS resources, things like listeners and routes, so that extensions must be careful when they try to access things that might potentially be garbage collected. So I'm going to pass back to, finally, this is how it actually looks in Istio. So the way we did this is by relying on an Istio config resources called Envoy filter. It's basically a static patch, so you can push it in between any control plane and Envoy, it just inserts a few filters. And these filters do the actual work. And what's notable here is this string at the bottom for runtime. This is how you select which runtime you want to use with either statically compiled in module or dynamically loadable WASM module, depending on which one you use.
Okay, so a lot of this work has actually landed in Istio 1.4, which released about 2 weeks ago, 1 or 2 weeks ago. And these are some of the numbers that we have. So the chart way on the right is if you use the mixer, the existing telemetry model, mixer v1. And the second one, the Prometheus plus HTTP Metadata Exchange, is what is already in 1.4. As you can see, it's already a significant drop in terms of CPU used. This does not include the CPU that Mixer itself used, which is actually almost equal to the proxy. So that's a significant CPU reduction. We're still in the process of, like some PRs are in, some are not, in the process of fully delivering the TCP protocol that Kuat described earlier. But we expect to get even better performance with that because now you're no longer exchanging headers all the time. There are still more optimizations that are lined up. So again, we expect to get this rich telemetry, but still be as close to just native base Envoy baseline as possible. So the next thing that we usually track and track often, and actually even other people track, is P90 and P99 for Istio. So as you can see on the right, it's the P99 chart. We always run baseline at the bottom, which means there is no sidecar at all. And then the next line over is just Envoy with nothing else. The line at the top was with Mixer. And as you can see, there is a significant drop. In this particular experiment, it's a 10 millisecond drop from what it used to be. So again, we have made significant progress in P99 latencies and also P90 latencies. And actually, I also have a demo. So let me, is that? Just going by what happened in the beginning when I was not demoing, I have some, okay, what the hell is going on here? It did? Okay, I have to stand like this now. Well, I think I'm just going to show the image that I've captured before because I don't think this way of navigating is working out. Okay, mirror display. Okay, great, all right. So, this is the live thing that's running right now. And, now, I am going to remove Mixer. So for HTTP, and I am going to create the telemetry v2 filters. Okay, so now that's the steady state usage. This includes both the CPU that's consumed by the proxy and telemetry. And very shortly, we should see both of them starting to go down. while it does that, I'm going to go back to the presentation. Okay, so the future direction is of course the work to, like all this work, like Kuat mentioned before, is in another repo in the Envoy organization, and the upstreaming work has already started. So finishing that is a big part of the overall work. We also want to add full support for network filters. This is only HTTP so far. Also, we want to add TCP support. We also want to improve language bindings. Everything is converging around open telemetry, so we want to make sure that the APIs are aligned with open telemetry, and then kind of align it further when open telemetry makes its way into Envoy, so that we have a nice path to export metrics. And then this will become the default extension model for Istio, in a few releases. Let me see if, okay, so as you can see, so the little bump there was the transients when both filters were kind of on at the same time, plus the churn that was caused by this switch. This switch is not a usual thing. I just wanted to bring out the fact that we are saving significantly on CPU. And now you see that way on the right-hand side, the CPU is going down. So the blue CPU on the right is the proxy, and mixer CPU just went down to nothing. So so like in all these measurements, it is a significant win. So summary, efficient metadata exchange imparts peer awareness, and we can build a whole lot of rich telemetry on top of that. Istio Telemetry v2 has made great performance gains in this release, and we will continue to do so. And the Google Istio team is adding WebAssembly support in Envoy, and that should be done in next quarter or two, thereabouts. And yay, this actually worked, so I'm glad.
So we have time for a few questions we can take, but before you guys leave, there's a survey form which you can fill for this talk from the schedule app, so we can take a few questions.
Hi, nice talk. We follow Google's best practices on like passing a context object with all of our gRPC calls, and it seems like OpenTelemetry covers part of the metadata in those context objects, and this would cover the rest of the stuff we pass. Is this a replacement for a context object?
So, not really. So, most of the OpenTelemetry, kind of the focus is instrumenting application code. This is slightly different because here you're using OpenTelemetry to instrument infrastructure code. So here it is going to be bound by like the overlying filter API and the alignment that we want to get with OpenTelemetry. So it's slightly different. I don't think it fully applies there. There is a context that is passed in the filter API, but it's not quite the same as the gRPC context.
Okay, thanks.
Hi guys, great talk. So maybe you guys answered it, but I didn't quite follow. Why did you need to do a WebAssembly like kind of code path or that binding? Why not actually include it into the main source code itself and make it like the default, right? Like, I mean, if you guys find it useful, like those 10 metrics, everybody around here will find it useful.
So the short answer is,
thank you.
So we primarily want to deliver it first to the Istio community. If the rest of the community finds it useful, then absolutely, we would love to upstream this as well. There is a separate benefit for all this WebAssembly work, because what you can do now is you can run stock Envoy, and you can deliver these WebAssembly extensions to the Envoy without recompiling it. What it does is it enables vendors and even bespoke filters that you may need in your organization to be compiled separately and pushed into Envoy. So this was a convergence of two streams of work. We could have done that separately, but it made a lot of sense to do it together.
Okay, thank you guys.
All right, thank you.